A quantum phase transition, QPT, is a shift in the state of a material at absolute zero temperature, driven by quantum fluctuations instead of temperature or pressure. Unlike classical phase transitions, such as water freezing into ice or boiling into steam due to thermal energy, QPTs occur due to changes in quantum mechanical parameters like magnetic fields or pressure. To visualize, imagine a tightrope walker, representing a quantum system, whose balance shifts suddenly due to slight changes in the wire's tension, the quantum parameter. Another analogy is a perfectly still pond, representing a quantum state, where a small pebble, quantum fluctuation, can create ripples that change the pond's surface dramatically. Real-world examples include superconductors, which exhibit zero electrical resistance under specific conditions, and quantum magnets, which change their magnetic state with varying magnetic fields. Additionally, materials like topological insulators can shift from insulating to conducting states on their surfaces, with slight changes in external conditions. In quantum Hall systems, electrons can form unique states under strong magnetic fields, leading to precise conductance changes. Bose-Einstein condensates, BCs. Another example occur when particles condense into a single quantum state under ultra-low temperatures, and QPTs can shift these condensates between superfluid and Mott insulator states. These QPTs are essential for understanding new materials and technologies, particularly in areas like quantum computing, advanced electronics, and materials science. In quantum phase transitions, we encounter a profound departure from our everyday experience, a realm where the rules of classical physics no longer apply. Unlike classical phase transitions, which are driven by changes in temperature or pressure, quantum phase transitions are governed by the principles of quantum mechanics. These transitions occur at the absolute zero of temperature, a realm of ultimate stillness where all thermal agitation ceases and the classical world fades away. Here, a different kind of energy comes into play: quantum fluctuations, which are the lifeblood of the quantum realm. These fluctuations, a fundamental consequence of Heisenberg's uncertainty principle, are ever-present ripples in the fabric of reality, constantly influencing the behavior of particles. They represent the inherent fuzziness of the quantum world, where even in the absence of heat, particles jitter and shimmer in a perpetual state of motion, defying our classical intuitions. It is these quantum fluctuations that drive quantum phase transitions, acting as the unseen hand that guides the system through its transformation. As we cool a system towards absolute zero, the delicate balance of energies within the system becomes increasingly susceptible to these fluctuations, making the system more prone to dramatic changes. Like a tiny nudge that topples a carefully balanced tower, these fluctuations can tip the system from one quantum state to another, triggering a dramatic transformation in its macroscopic properties, much like a sudden shift in a dance routine. Imagine a dance floor filled with dancers, each swaying to their own rhythm, creating a scene of beautiful chaos. At high temperatures, their movements are chaotic and uncoordinated, reflecting the disorder of the system. But as the music slows and the temperature drops, a sense of order emerges, and the dancers begin to find a common rhythm. The dancers begin to move in sync, their individual motions merging into a collective, synchronized flow, much like particles aligning in a new quantum state. This, in essence, is the essence of a quantum phase transition, a process where the system undergoes a profound change, revealing new patterns and structures. It is a dance of uncertainty, where the random jiggling of quantum fluctuations orchestrates a transition from one ordered state to another, revealing the hidden symmetries and emergent properties of the quantum world, a world that continues to surprise and inspire us with its complexity and beauty. Imagine a tightrope walker carefully navigating the narrow path between two skyscrapers. Each step is deliberate, calculated, and fraught with tension. The walker must maintain an extraordinary level of focus and balance to avoid a catastrophic fall. At the precarious midpoint, the walker stands at a point of perfect balance, a critical point where even the slightest gust of wind could send them tumbling in either direction. This moment of equilibrium is both fragile and powerful, embodying the essence of tension and potential. In the quantum realm, we encounter a similar concept, the quantum critical point. This is not just a theoretical construct, but a tangible phenomenon that scientists can observe and study. This is the point at which a quantum system teeters on the brink of a phase transition, where the competing forces of order and disorder are locked in a delicate stalemate. The system is in a state of flux, ready to tip into a new phase with the slightest nudge. At this critical juncture, the system exhibits remarkable sensitivity to external stimuli. The instruments used to measure these changes must be incredibly precise, capable of detecting even the most minute variations. Even the tiniest perturbation can have dramatic consequences, tipping the system into one phase or another. This sensitivity is what makes the study of quantum critical points so fascinating and challenging. This extreme sensitivity gives rise to a plethora of unusual and intriguing phenomena, making quantum critical points a hotbed of research and discovery. Scientists are constantly uncovering new behaviors and properties that challenge our understanding of the quantum world. One of the most striking features of quantum critical points is the emergence of long-range correlations. These correlations are not just theoretical, but have practical implications for how we understand and manipulate quantum systems. Imagine a stadium full of spectators, each holding up a colored card. At first glance, the scene appears random and chaotic, with no discernible pattern. At random, the stadium resembles a chaotic mosaic of colors. Each person acts independently, contributing to the overall disorder. But then, a wave of coordination sweeps through the crowd and suddenly, intricate patterns emerge, spanning the entire stadium. This transformation from chaos to order is both mesmerizing and profound. This is analogous to what happens at a quantum critical point. The system transitions from a state of disorder to one of coordinated behavior, driven by underlying quantum mechanics. The normally localized interactions between particles become amplified, extending across vast distances. These long-range interactions are a hallmark of quantum criticality, revealing the interconnected nature of the quantum world. This long-range entanglement leads to the emergence of novel collective behaviors, akin to the synchronized wave in our stadium analogy. These behaviors are not just curiosities, but hold the potential to revolutionize our understanding of quantum systems and their applications. The quantum magnet, a tale of two states. In this section, we will explore the fascinating world of quantum magnets and their unique properties. To grasp the essence of quantum phase transitions, let's delve into a concrete example: the quantum magnet. This example will help us understand the underlying principles and behaviors that govern these transitions. Imagine a lattice of tiny atomic magnets, each with a north and south pole, like miniature compass needles. These atomic magnets interact with each other in complex ways, influenced by both thermal energy and quantum mechanical effects. At high temperatures, these magnets are in a state of thermal chaos, their orientations randomly fluctuating. The thermal energy is so high that it disrupts any potential order among the magnets. As we cool the system down, something fascinating occurs. The thermal energy decreases, allowing quantum mechanical interactions to become more significant. The interaction between neighboring magnets, a purely quantum mechanical effect, starts to dominate. These interactions are crucial in determining the overall behavior of the system. Below a certain critical temperature, the magnets spontaneously align themselves, all pointing in the same direction. This alignment is a result of the quantum mechanical interactions overcoming the thermal chaos. This collective ordering of atomic magnets is known as ferromagnetism. It is a phenomenon where the magnetic moments of the atoms align to produce a strong, uniform magnetic field. It is a macroscopic manifestation of a quantum phase transition, driven by the interplay of quantum fluctuations and interparticle interactions. These interactions are delicate and can be influenced by various external factors. The once disordered system has transitioned into a highly ordered state, exhibiting a macroscopic magnetic moment. This transition is a clear example of how quantum mechanics can influence macroscopic properties. Now imagine applying a magnetic field to our quantum magnet. This external field can interact with the magnetic moments of the atoms, further influencing their behavior. At high temperatures, the field has little effect on the randomly oriented magnets. The thermal energy is still too high for the field to impose any significant order. However, near the quantum critical point, the system becomes incredibly sensitive. The balance between thermal energy and quantum interactions is delicate, making the system highly responsive to external influences. Even a tiny variation in the field can drastically alter the magnetic order, flipping the direction of magnetization or even destroying it altogether. This sensitivity is a hallmark of quantum criticality. This extreme sensitivity near the quantum critical point has profound implications. It suggests that quantum materials can be finely tuned and controlled, offering new possibilities for technological advancements. It suggests that by carefully tuning external parameters, we could potentially control and manipulate the properties of quantum materials with unprecedented precision, paving the way for novel technologies and applications. This level of control could revolutionize fields such as quantum computing, material science, and beyond. When worlds collide, dissipation enters the stage. So far, our exploration of quantum phase transitions has unfolded in a pristine, isolated world, where quantum systems evolve undisturbed by their surroundings. However, in reality, no system is truly isolated. The quantum world, like a ship at sea, is constantly buffeted by the waves of its environment. This interaction with the environment leads to a phenomenon known as dissipation, the gradual loss of energy and coherence from the quantum system. Imagine a pendulum swinging back and forth, its motion slowly dampened by air resistance. Similarly, dissipation acts as a drag on quantum systems, causing them to lose their delicate quantum properties over time. In the context of quantum phase transitions, dissipation introduces a new layer of complexity. The interplay between quantum fluctuations, interparticle interactions, and environmental coupling gives rise to a rich tapestry of novel phenomena, challenging our understanding of quantum matter. For example, dissipation can drive quantum systems into entirely new phases of matter, not accessible in isolated systems. It can also influence the dynamics of quantum phase transitions, leading to exotic critical behaviors and the emergence of novel quantum states.